people always blame meteorologists for being wrong, but it's actually impressive how right we are most of the time. And so this is a plot showing the forecasting track accuracy, so how accurate we've been doing in the past 40 or so years since we started doing track forecasts.
So today we have three very special guests. Our first is Sydney Sroka. She's a PhD candidate with Professor Carrie Emanuel at MIT. Her expertise is in computational fluid dynamics, and she studies the air-sea transfer of enthalpy and momentum in the hurricane spray layer. She received a National Science Foundation Graduate Research Fellowship upon entering graduate school and hopes to continue studying air-sea coupling after she graduates. And then we have Tom Beucler, who's a fourth-year PhD candidate in atmospheric science affiliated with the Lorenz Center at MIT, who is co-advised by Timothy Cronin and Carrie Emanuel. His expertise is in environmental fluid dynamics and atmospheric physics, and is interested in the way radiation influences a hurricane's growth rate and intensity. And last but not least, we have Jonathan Lin, who is a graduate student with Professor Carrie Emanuel. He graduated from Princeton with a Bachelor's of Science in Computer Science last year, and for his PhD is studying hurricane predictability. Jonathan is both an American Meteorological Society and a Rasmussen Fellow. Sorry. So without further ado, I'm going to introduce Sydney, Tom, and Jonathan to come on up. So go ahead.
Thank you so much, Gina. Thanks for having us. We're really excited to talk to you today about hurricanes and what they are, and how climate change is expected to change the types of hurricanes we might see in the future. Let's start really basic with just what a hurricane is. Is it just a big storm? Is it just a big spinning storm? A hurricane is an organized, nearly symmetric cluster of thunderstorms that's rotating about a low-pressure center. These storms all originate in the tropics, and that makes hurricanes part of a class of storms known as tropical cyclones. The 2017 hurricane season was one of the most devastating in history for the United States. Over $200 billion worth of damage between Hurricanes Harvey and Maria. And you can see Hurricane Harvey on this diagram. Its trajectory started in the tropics, along with other hurricanes from that season. So hurricanes are named. The first hurricane of the season has a name that starts with an A, and then we go through the alphabet for the rest of them. And I keep saying hurricane season, and that's because hurricanes are most common in the late summer and early fall. And this is because the sea surface is warmest at that point of the year. And a warm sea surface helps a hurricane intensify. It's a more favorable condition for hurricane formation. And that's a really powerful thing to know, is how hurricanes form and what makes them stronger and what makes them weaker. And that helps us predict them better. So first, what makes a hurricane stronger? Well, I've already said, if you have a warmer sea surface, a hurricane's going to be stronger because it extracts energy from the warm sea surface. So the eye wall of a hurricane has very strong winds. It's about a 10-kilometer wide section of the storm, and it churns up lots of ocean water, creates lots of sea spray, and that warm sea spray, it's about 80 degrees Fahrenheit, evaporates and gives off its heat to the wind above to help power the hurricane. My research is right in this zone. I'm studying the efficiency with which heat is extracted, and if we know that better, we can improve the models of hurricanes. Second thing that'll make a hurricane stronger is when the air is very humid. Humid air will contain more energy than dry air, and that will help power the hurricane also. So what makes a hurricane weaker? Well, the first thing is if the hurricane begins to tilt over, and maybe you've seen in the news like strong shear winds or having strong shear. Means that at the top of the hurricane you'll have very strong winds, and then below they won't be quite as strong. And that makes the eye wall tip over, and that's a much less efficient path for the hurricane to circulate air. Also, if the hurricane begins to tip over, it will start entraining dry air much more than it would otherwise. The last thing is when a hurricane makes landfall. So you noticed in the 2017 hurricane diagram that I showed before, as soon as a hurricane hits landfall, its category drops precipitously. And that's because you've shut off the heat transfer into the atmosphere above. There's lots of drag, it takes lots of energy to push trees over. and that's where the energy goes. And landfall is one of the most dangerous stages of a hurricane's life cycle for coastal populations. It's something that we're really interested in. So when we talk about when it makes landfall, we want to know the track. We want to know where it's going to end up making landfall and how intense it is when it gets there. So this is a diagram of hurricane tracks from 1851 to 2006. You can see each individual filament shows a given hurricane. And the path is the path that's traced by the eye of the hurricane. The colors correspond to the intensity. The intensity is a proxy for wind speed. So intensity is the maximum wind speed that's observed for at least 1 minute. The Saffir-Simpson scale, something that you might be familiar with, Category 1 hurricane versus Category 5. And it's an incredibly simple way to bin hurricanes. So each category is about 20 miles per hour wide. And you just take the maximum intensity that you observe, and you see which category it falls into. It's a proxy for damage, and the advantage of the Saffir-Simpson scale is that it's simple, but something unfortunate about it is that it's probably too simple. Hurricanes are incredibly complex. They have lots of ramifications: storm surge, rain, and wind. And boiling all of that risk down into one number is a little bit complicated and maybe not totally accurate, or not the best way to communicate to the public. But because it's so simple, it is useful, and wind speed is correlated with damage. So in order to best predict, Jonathan's going to talk about how we go about predicting this complicated process.
So I'll talk a little bit about hurricane prediction. It's kind of what I work on. So all the predictions in the United States are overseen by the National Hurricane Center, which is a subsidiary under the National Oceanic and Atmospheric Administration. It's down in Florida. And there they have, when a hurricane forms or is going to track near the United States, we have very, very bright meteorologists who are trained in understanding the weather. And we have these weather models, which are run on giant supercomputers, which kind of try to solve mathematical equations and predict what the state of the atmosphere will be in the future. And these, we have tons and tons of different models. Each might say a little different thing because each model has a different quirk. And it's the job of the scientists to make an educated prediction. So their job is to understand what is going on in the atmosphere and which model's right, which model's wrong. And so they take all this information and make a prediction. One of the hardest things to predict about hurricanes is actually the intensity. So how strong, as Sydney mentioned earlier, how strong the wind speeds are in these hurricanes. And we actually, in the United States, we measure this by a 1 minute sustained average wind speed. And you might have seen on the news this past winter, especially here in Boston, this term called bombogenesis or bomb cyclone. We just stole this from this headline from a Time article, Winter Storm Riley. And here is a satellite picture of Riley when it was affecting the United States. And although this has many different characteristics than a hurricane, there is actually an equivalent to bombogenesis for hurricanes. And by bombogenesis, I mean this rapid intensification of a weather storm. So we'll see a video of this later. But there's an equivalent for hurricanes called rapid intensification, and this was quite common last hurricane season. Hurricane Maria underwent rapid intensification. So a hurricane can go from a Category 1 hurricane to a Category 5 hurricane very quickly, and that's actually very, very dangerous. Yeah. So the actual definition for bombogenesis is 24 millibars of pressure in 24 hours. Pressure is, people will call these storms low pressures because they're centers of low pressure. Any other questions? So here is if it loads, infrared imagery of Hurricane Maria. So it starts out as a cluster of thunderstorms. You can see the brighter colors are just where precipitation is occurring. And it's not really spinning and organized yet, but then in a matter of maybe 12 hours, 12 to 24 hours, Hurricane Maria goes from a disorganized set of thunderstorms to a very, very, very strong, rapidly rotating hurricane. And this is what rapid intensification of hurricanes is. So we want to go about predicting where these hurricanes will go. And this is very important for warning coastal communities which are especially at risk, like in Florida. And so I'm not sure how many of you might have lived down south. Hurricanes aren't as common up here. But if you've ever seen a forecast, the National Hurricane Center outputs these forecasts, which you can think of as a cone of uncertainty. So this is kind of a measure of where we think the hurricane can go. So as the cone widens as we go further out in time, and they put out a bunch of all these different risks for hurricane warnings for places that might be affected. And this is to show our uncertainty in the forecast. We aren't always right all the time, and we'll have some measures for how well we're doing in terms of hurricane forecasting later. Any questions? So we can also combine our uncertainty of where the hurricane will go, so the track, as Sydney mentioned earlier, as well as with how strong the hurricane will get. As I mentioned, cyclones can go under rapid intensification or other processes like shear that can weaken the hurricane. And so we can combine all these probabilities into, sorry, the color is kind of blotted out, but you can combine these to get probabilities of tropical storm force winds. So it's kind of a mouthful, but what it means is what is the probability that a certain place will receive tropical storm force winds within the next, and this graph is within the next 5 days. And so here, this is for the same exact forecast of the cone of uncertainty that I showed you last slide. But it's combining our uncertainty with how strong the hurricane will get and where it will track. So you can kind of see the cone of uncertainty here, but also the intensity of the hurricane is also hidden inside these messages. And this is what the National Hurricane Center is really, really trying to move towards, rather than this cone of uncertainty, because you can get hurricane force winds many, many miles away from the center of the hurricane. And so this is actually much better in conveying to the public the danger or where you might receive dangerous conditions. So how well are we actually doing with forecasting? People always blame meteorologists for being wrong, but it's actually impressive how right we are most of the time. And so this is a plot showing the forecasting track accuracy, so how accurate we've been doing in the past 40 or so years since we started doing track forecasts. The dashed lines are just linear fits on the errors for each lead time. And when I say lead time, I mean you can see the 12-hour, 24-hour, et cetera. And that's how far ahead we're forecasting. So the red line shows our error in nautical miles for a 12-hour forecast, so forecasting 12 hours ahead of the storm. And here we see we're actually doing really great. We've been improving very markedly over the past 40 years, and it's only getting better. And for track, at least, we're doing really, really well. Intensity, however, as I alluded to, is a totally different story. This is the same plot, but for intensity of the hurricane, for the same amount of lead times. And there's not as much of a decline in the error over the past, since we started doing intensity forecasts in 1990. And that little dip you see there with the blue and pink colors is not statistically significant. And the errors are not actually improving as fast as we'd like. And so it's very important more research is being done in improving the forecasts of hurricane intensity, and Tom and Sydney's work also will help with that. And so as you saw, there is actually no such thing as a cone of uncertainty for intensity as there is for track, because it's so hard to forecast. You need big supercomputer models to forecast the intensity. And so our advisor has made, or recently, this is kind of the state-of-the-art research. This was made just last year. It's a very, very simple simulator for hurricanes. It can be run on your laptop, as our advisor likes to say. And instead of using a big supercomputer, you can give this model a track, so where the hurricane will go, and it'll output the intensity of the cyclone. So here, I've, just for a sample forecast, we've color-coded the tracks with how intense the storm will get, the intensity of the storm. So here, as we see that as the storm travels northwestward, it decays in intensity. And so models like this are kind of the way forward in doing risk analysis or probabilistic forecasts for hurricane intensity. And they really are the cutting edge of how we're trying to understand how hurricanes intensify. And we really want to bring that error down. And so because or as Sydney alluded to earlier, hurricanes intensify as a function of their environment. And as we know, the environment isn't the same, where humans are changing the climate. And so we want to understand how hurricanes, or the intensity and where they go, might change under a changing climate. And Tom will speak about this.
So on to the most controversial yet fascinating topic of the night, which is how are hurricanes expected to change with climate? And so what I'm showing you here is a satellite picture from NASA ATS-3 geostationary satellite from exactly 50 years ago. So, sorry, I'm gonna loop again. So as you can see, we were getting our first satellite pictures at the time, and this is a satellite that took the first color photography of the Earth. And if you remember the pictures that Sydney has shown you earlier, you can notice a clear difference in resolution. And that is a good proof of why we cannot use our past observations of hurricanes to predict how they will change in the future. It's because we have made so much progress in observing hurricanes in the past 50 years that only the last 20 years can really be used if we wanted to compute a trend. So because we can't observe those hurricanes and deduct how they will change with climate, we have to rely on physics. Some of its physics has been established for 2 centuries, the law of thermodynamics, and some of it is fresh new, and we're just starting to figure it out. And so I will start with a more established example, and that is the example of the Carnot cycle. And that's a cycle that allows you to evaluate how efficient the heat engine of your car is, but also how efficient your fridge is. So what you can see is there's 4 different phases. So I'm showing it with a piston here. At first, the gas expands as it is heated. Then you let it expand by itself. Then you cool it, and it's going to compress. And then you let it compress by itself. And this process allows you to produce work. And that's, for example, a good way of evaluating the maximum power you can get from heat engines. And the really fascinating thing is you can use the same physics, the same model, to evaluate how a hurricane can intensify and how a hurricane can extract energy from the ocean. And so it's a very similar process. As the air flows in the hurricane, it is heated by the ocean and it expands. Then it's going to expand as the air rises up. And once it's up in the atmosphere, it is going to cool by emitting energy in the form of radiation to space. And then finally, it's going to flow back in and be compressed. And by using this simple model, we can know the maximal potential intensity of a hurricane. because we know the maximal heat it can extract from the ocean, and then you can quantify how big the winds can be. And so we know an upper bound on how large the surface winds can be. And then what we can do is we can look at some of the best global climate models, and here I'm showing the one from the GFDL laboratory in Princeton, which is arguably one of the best American global climate models. And what it predicts is that you can see all this red in the Atlantic basin, is that because the sea surface temperatures are getting warmer, you can extract more energy from the ocean. And because that happens, the winds, the maximal winds, are expected to get stronger and stronger, and you can see up 2 meters per second per decade. And so by the end of the century, it's up 20 meters per second. And so this is a result we can get from very, very old and established law of thermodynamics. And now in contrast, I wanted to show you something much more recent. So that's a result from a paper that was published just 2 weeks ago in Nature. And we're still trying to figure out the real physical reason of this result. But what that paper says is that hurricane motion is going to slow down as the climate warms. And here is the last Atlantic seasons that Sydney was showing you on the slide earlier. And what you can see is Harvey, which is a very, very harmful hurricane. And now it's approaching Texas. And the really interesting thing with Harvey is that it was really, really slow as it approached and made landfall in Texas. And because it was so slow, it drained a lot on Texas. And it led to up to $125 billion of damage. And of course, we can't take a single example and make it a generality, but what we know is that very slow hurricanes are very harmful. And so that if that happens, we might expect the total damage done by hurricane to increase by the end of the century. And then the last really cool result is that the tropics, as the climate is warming, the tropics are going to expand. It sounds really interesting, but it does have some dramatic consequences. And one of the plausible consequences it may have is that hurricanes are going to move poleward as climate warm. And they're going to move even more polewards than the tropics are going to move poleward, because if you remember what Sydney told you about the tilt, the zone of maximal tilt is also going to move, and the air is going to be moisture. And so right now, the latitude where hurricanes do the most damage is around 20 degrees, and we expect it to move up to 25 degrees by the end of the century. And that will significantly increase the average damages done by the most intense hurricanes, at least in the United States. And that's where we are. That's where Boston is. And since hurricanes are expected to move poleward, we also expect the damage in higher latitudes, like the city we live in, to increase. And that's what we've been trying to work on with my office mates. We've been starting since this year to do flood risk analysis and climate risk analysis for the city of Boston. So I'm going to zoom in. This is New England, and I'm going to keep zooming in. And what we started to work on was the risk for the MIT campus. And so I'm going to zoom in even more and show you a very simplified pipe network of the MIT campus. And what we do is we run thousands and thousands of hurricane cases, and then we select the most harmful cases, and we feed them to a storm surge model, and so we know how high the Charles is going to get. And once the Charles is really high, the pipes of the campus are going to flood, and the campus is most likely going to flood because of the pipes that will not be able to evacuate the storm waters anymore. And this is how it, sorry. Oh. So once you run the hydrology model of the pipe, you can look at the flood water in on the MIT campus as a function of time, and you can see and predict roughly how the MIT campus is going to flood. And the really interesting thing is you can do the same work for many different cities and coastal communities and look and evaluate the communities that are most at risk under a changing climate if you know what the most harmful storms are going to look like by the end of the centuries. And so hurricanes are coming, but a lot of us are working hard to help us prepare by having real quantitative analysis of the flood risk, the statistical flood risk that we are all going to face as coastal communities. Thank you all for your time and have a great evening.
Hi. So that's really great presentation. Thank you. I learned a lot. What I'm curious about is, as you mentioned, there's a lot of uncertainty, and there's a lot of sort of consequence for what could happen when the hurricane hits a populated area. So, and I really liked how you showed the uncertainty, but I'm wondering, for non-scientists, I mean, there's the general public, but then there's also like the, I guess, local governments that have to be prepared. Has anyone tried to figure out or study or survey what information about uncertainty they'll actually act on and respond in a rational way and take the precautions proportionate to the level of uncertainty?
Yeah, so that's a really interesting question is we could give this bound of uncertainty, but then like what does the public know or how do they react? And it's a really hard problem. It's something that some leaders in the field have wondered whether or not we could have maybe a more complicated system for describing the uncertainty, but then only officials that are in charge would really need to understand it. And that's sort of one avenue to pursue. Another one is that the rating system itself is a little bit simple. And that's good because simple things have a lot of inertia and they're easy to understand. But with something as complicated as a hurricane, it might be detrimental. So when Hurricane Sandy made landfall, I don't think it was a hurricane anymore. I think it had gone down to either a tropical storm or it was now a Category 2. And the mayor started to halt evacuation procedures. And after he got lots of phone calls from people that were predicting the level of damage that was there, he reinstated the evacuation procedures. And it's a classic case of communication failure. And so I know that leaders in the field are working on sort of how to establish something that's easy to communicate risk, and maybe a succinct statement of specific risks like storm surge are the best way to go.
Hi, so I assume there are a lot of variables behind all of these models, and so in terms of just if you could speak on meteorology a little bit of like, what are the components when a storm's coming that are feeding into various models? Like, is it, are they testing temperatures in different areas? Like, what are the actual physical pieces that are feeding in to predict hurricanes?
So most of the flood risk comes from the storm surge. So that's the elevated level of the seas that comes because of the strong storm winds. So if you didn't have any better information, you could just use the storm wind field and then run a big hydrological coastal model to see how high the sea is going to be and then how it's going to flood. But ideally, what you would also have is precipitation. Precipitation is a little harder to predict, but once you have precipitation, you can capture interesting effects. So for example, we in Boston, and if it rains upstream in the Charles, it's going to make the Charles much higher. And so then when you have a storm surge coming from the sea, flanking the Boston Dam from the two sides, if the Charles is already higher, then you're going to flood the entire, for example, South Boston and all the lower region of Cambridge much, much faster. So you would start with wind. If you have precipitation, it's even better. And I see you mentioned temperature, and that also enters in the model, but that's not as important. But if you have it and you can feed it to the model, then you increasing the confidence you have in predicting this final flood height and the flood risk. Does that answer your question?
I was going to speak more about operation.
Oh yeah, sure.
If you wanted to know more about how it works operationally, and what I mean by that is day-to-day forecasts of hurricanes. So we have these big weather models, and a lot of data is going into these weather models to help them predict the atmosphere. So we fly airplanes into hurricanes and drop balloons that measure different properties of the air around it. So for instance, humidity, temperature, you mentioned. And that all feeds into, so we take out satellite data, radar data, we take all of that and feed it into a model. In terms of actually predicting, when we look at where a hurricane will go, scientists, our meteorologists are looking for what is the steering wind. So what are the winds, where are they trying to push the hurricane towards? And intensity, as Sydney said, can vary a lot on shear. So that involves trying to know what the winds are in your atmosphere, so where they're going to push the storm, what the temperature of the sea surface is of the ocean. We can get that from satellite data. And precipitation, as Tom mentioned, near land regions where we have machines on land that can send out, it's basically they send out particles of light to try to see how it scatters, and raindrops scatter in a different way than clear air does. So we can see how hard it is raining, and that can also get fed into one of these models.
You sort of started to address this, and maybe you kind of did already, but what can you say more about why intensity forecasting is so fundamentally more difficult than track forecasting, if that's even really fully understood?
I think it's because forecasting the intensity of the hurricanes means you understand this and model the structure of the hurricanes very well. And it involves a lot of physics that first we can't really observe. It's really, really hard to get any observations in hurricanes because the winds are so violent that a lot of things just get destroyed if you try to send them in the hurricane. So you can drop sounds and hope they don't get completely destroyed. And we have recently gotten some of the first, during World War II, for example, some of the bravest pilots would just try to fly through a hurricane and hope to get through it and maybe give you some really important information that you can then feed in the model. But nowadays people don't do that anymore. So we can fly drones through hurricanes, and that's maybe. Yeah, I mean, it's a hard topic. And then when you go to the modeling side, and that's a lot of what I work on, we don't understand a lot of the physics as soon as water vapor and a lot of turbulence is involved. And so, for example, we're still debating as a community what makes a hurricane start and become more intense. We still don't agree on the most important physical mechanism, and we still have a really hard time modeling them in practice. So that's why I think a lot of the uncertainty is still there.
Some of it might also be a semantic thing. The United States defines intensity as the 1 minute sustained average wind that we observe. So it also depends on where you observe the hurricane, or where in the hurricane you observe. Other countries use a 10-minute sustained average wind. You can ask yourself, well, why do we use these horrible definitions of intensity? A hurricane is much more than just wind speed averaged over 1 minute at one particular location. So that's why we're trying to move away from this single measurement of intensity and do more of this probabilistic forecasting, as you saw, because that gives a much better understanding of the impacts of the hurricane rather than, its maximum wind speed is 130 miles per hour, for instance.
Thank you for the sharing. My question is pretty much related to the previous one. So now if I can give you anything you like, what would you choose to have in order to predict the hurricanes better?
Well, we all do slightly different things. So selfishly, I would want data in the zone that I study, which is the spray layer. But that might not be for everybody. Although the spray layer is pretty important. It's where it gets most of its energy from. Oh, yeah, sure. So like maybe the first, say, 10 meters. So in regular, you have like an air-sea interface when you look out on the ocean from Boston Harbor, right? Doesn't exist in a hurricane. Hurricane, the wind speeds are so fast, you just have lots of bubbles, and then you have lots of spray, and there's no clean interface. And that's really interesting physics, because if you have lots of tiny drops with characteristic length scales of 100 microns, and those are the intermediary in the hurricane eye wall, which is this 10-kilometer wide zone. It spans a lot of scales very quickly. So if I could have any data that I'd want, I would really like an underwater vehicle I think that'd be cool to like go and observe the spray layer and give me drop size measurements and give me temperature and humidity in that region. That would be cool. Do you guys have your dream data?
I have one, but yeah. So as Sydney say, we study slightly different thing, and I study a lot how the energy gets moved around and how the energy amplifies. And so the observations we have right now are satellites, so we can look from the top very well. But then most of the energy is concentrated in the bottom. So if you look at the top, like 2 or 3 kilometers, because it's so humid, you have a lot of energy in the form of water vapor. So you have a lot of water vapor. The air is very, very humid. And so if we could have a way to measure water vapor and temperature in this bottom 3 kilometers, we could complement the information we get from this satellite. And so, for example, we have LiDARs that are very, very good that you can deploy on the ground, and then you can measure temperature and water vapor. That would be super helpful. But you're not going to deploy a super expensive instrument when there's a big hurricane passing by. Otherwise, you may lose a lot of money. But ideally, if we could find a way to measure those variables, then we could answer a lot about cyclogenesis and how hurricanes really amplify quantitatively. You would have a much better idea of the rate. Do you have anything?
The position and velocity of every single particle in a hurricane.
So maybe this is a not so relevant question, but I would like to know if there are any difference between the typhoon in Pacific Ocean and hurricanes in Atlantic.
Do you want to take this one? I can take this one. There's the exact same phenomenon in terms of physics. They're both tropical cyclones. It's just that we call the tropical cyclones of the Atlantic hurricanes, and we call the tropical cyclones of the East Pacific typhoons. West and, oh yeah, East Pacific is still the US. Yeah, sorry. West Pacific are typhoons, and then Indian Ocean, we just call them tropical cyclones.
Hi. I've noticed in the last few years that when you look at a storm and actually the hurricane itself, Hurricane Harvey, as they are in the Florida area, they come in through inland and they keep their power for so long. But then they can actually, as they turn different directions, they can either continue upland into land or come back in. Now, when if they come back out to land, are they able to continue to grab more power from the ocean currents, and then if they can go back into land, are they able to do that?
Yeah, if a hurricane goes over land for a short enough time that it's not fatal to the hurricane. Like we saw that in Hurricane Harvey, right? It went over a part of Central America and then was able to keep going until it hit Texas. So definitely. And you mentioned Florida, how it can be over land for a little while. Same thing happens in Louisiana. If you have more swamp-like conditions, your land is closer to ocean than it is to other types of land that the hurricane could potentially encounter. So the more ocean-like that land is, the longer it can be sustained over that region.
So what are the most important differences between tropical hurricanes and winter storms? Because you almost presented them like they were very similar, but they must be different because it's so much colder away from the tropics.
They're different beasts in the sense that extratropical cyclones are much bigger in terms of scales, and so they are very tied with the circulation of the atmosphere on the planetary scale. So they very influenced by the way the Earth rotates, and they all form, they all follow the same wave pattern and propagate to the east at our latitudes. Tropical cyclones are much smaller, more compact. They're not as they're not tied as much to the large scale pattern, and they take energy from the tropical oceans and from the Earth rotation, and then rapidly intensify, and then will move poleward, which is very different from the extratropical cyclones, which are mostly just going to move east regularly. So that's a really good question. Because tropical cyclones are more compact and kind of they have their own little beasts. Then if you understand how tropical cyclones work, you can make predictions on how they're going to change with climate. So what we have shown you earlier. With extratropical cyclones, it's a much more controversial topic. A lot of people think they're not going to change that much with climate. Some people think the mean intensity might go down. We have reason to believe that when the model will be high enough resolution, we might have more extreme events, but it's still a very controversial topic. Whereas if you're talking about tropical cyclones, I think the whole community agrees that we're going to get more extreme tropical cyclones, even if the total number may go down a bit. That's for sure in the West Pacific. In the Atlantic Ocean, it's a little more controversial, but I think it holds as well. Do any of you want to add anything?
I think the main difference is these winter storms are driven by the large-scale environment, as Tom said. Maybe temperature gradients is maybe a good proxy, whereas hurricanes are driven solely by the surface of the ocean. Or that's where the power comes from.
So just to follow up on that, I mean, the rapid intensification of winter storms versus the rapid intensification of hurricanes, that's driven by a completely different process, or is it believed that, in fact, at sort of the small scale, they're in some way closely related?
I wouldn't say that they're completely different, but definitely the mechanisms for a tropical cyclone is definitely a surface effect, so they're gaining their intensity from the surface. For extratropical cyclones, or these winter storms, which you call extratropical cyclones, so extra meaning out of the tropics, they definitely get their strength from many different areas. So one could be temperature gradients in the atmosphere. Another can be vertical wind shear. So how, as Cindy said earlier, winds at the lower level might be slower than the winds at the upper level. You can. Temperature gradient meaning it might be. For instance, we don't have the satellite picture anymore, but for these very intense winter storms, you usually have very, very cold air to the west and very, very warm, humid air to the east. So as the air flows up from the south, it grabs this very humid, warm air, and the warm air rises, and that's why you get so much snow and precipitation, and then the cold air sets in behind it. So often you'll see very cold air behind a winter storm.
Yeah, I think the rapid intensification of hurricanes is also different in the sense that it can be influenced not more locally by the energy it receives from the ocean, but it might also, and that's a topic of it's a controversial topic, and that's also what I'm researching. It might also be influenced by the clouds that are formed by the hurricanes and how much it prevents the hurricane from losing energy to space. And so that is not as prevalent in, for example, the winter storms that are much bigger events, which don't have as much of an intense cloud cover that hurricanes have. So there are a lot of cool research topics around that topic.
Cool. Let's give them a round of applause. Thank you. Great. So if you thought this talk was really interesting and you want to learn a little bit more about hurricanes and potentially how hurricanes could be changing with our climate, NOVA has a new special that's coming out next week. It's called Rise of the Superstorms. It is airing at 9 o'clock on your PBS station. And if you can't watch it on your TV, it will be streaming on our website if you look for NOVA. And we have a sneak peek clip, so you will get a special viewing of Rise of the Superstorm. So it's just a 2-minute clip, and we'll be showing it on screen. So Sydney, roll it.
Unprecedented devastation.
By Friday morning, they started using the word catastrophic.
3 monster hurricanes in a single month. Harvey, Irma, Maria.
If you're told to evacuate, get out quickly.
They strike violently, scouring the land.
We saw winds in excess of 190 miles per hour.
The eye was right here on top of us,
Leaving devastation and thousands stranded in their wake.
Today, the focus is on rescue.
Houston, the nation's 4th largest city, is underwater.
We know that people are facing really catastrophic situations. They may be fighting for their lives.
Islands like Puerto Rico and nations of the Caribbean are ravaged.
The entire country has been decimated. I have never seen anything like this before.
The Florida Keys are in shambles. What explains one of the most disastrous hurricane seasons on record? Why did the strength of these storms take so many by surprise? Could a warming planet be driving the weather to new extremes? Are storms of this intensity the new normal? And how will we cope?
Many organizations talk about climate refugees. 2017 Atlantic hurricane season may have ushered in that era.
For the survivors, life may never be the same.
This is unreal.
Here was the living room right here.
I couldn't believe what was happening to us. We lost everything. Everything.
Rise of the Superstorms, right now on NOVA.
So we will be here next